Hi guys, welcome to the assignment 2 walkthrough video for COSC 330-530, and today we're going to walk through assignment number 2, which is our Nordvig suspension bridge problem. And for this assignment you're going to be writing a multi-threaded C program that implements a simple system of semaphores to ensure we have synchronized mutual exclusion to a shared resource. And so to start off with here, we're going to talk about the problem, and essentially this particular assignment is a variation of the readers and writers synchronization problem. So the essential concept is that we have some shared resource and we need to synchronize access to that shared resource. So in a classic computer science context, this is usually a piece of data such as a shared variable. And so we want to we want to have read access to that shared resource where multiple processors or threads can read it at any time. But if we're writing to that resource, that shared piece of memory, then writers should have exclusive access. And we solve this problem by using what we call binary semaphores. We've covered these in the lectures, but here we have some simple algorithms. As I said before, this should be a bit of a revision from what you've seen in the lectures. But here we have our shared integer that keeps count of the number of readers. We have our data lock, which is our shared lock item, and our actual shared data. This is the resource that we want to access to. And so for the reader algorithm, we lock our our lock count. So we have to, because the count itself, the reader's count itself, is a shared resource, we have to lock that. We increment it, and if it's the first reader in, we lock our data up, then we unlock our lock count, we read our data, and then we lock our lock count and decrement our counter, and then we go through and proceed to unlock the data if we're the last reader out. So it's important to remember that a reader will block out exclusive access to a writer. So if we're the first reader in, we have to lock our data, and if we're the last reader out, we have to unlock our data, and at the end we of course unlock the count lock. The writer algorithm is really simple because a writer needs exclusive access to our resource, so you can only have one process or one thread writing data at a time. We have an exclusive lock on that, so our writer algorithm just jumps on in, it attempts to lock the data lock, it writes to the data, and then it unlocks the data lock at the end. And of course, when we're attempting to obtain these locks, our program needs to block and wait until we can do that. And so that introduces the concept of the readers and writers problem. So we want to extend this in our assignment to the Nordvig suspension bridge problem, which is essentially a readers and writers problem where we have different classes of threads or processes trying to access our shared resource, which is our bridge. So our bridge is essentially our data item, and our cars are akin to reader locks. So we have cars going east, cars going west, and we have trucks, which are analogous to a writer lock. And your task is to modify or implement a system of semaphores that reflects this scheme. So we can have up to 3 cars traveling on our bridge at one time, or we can have multiple cars, sorry, traveling on our bridge at one time. Here in the diagram, I've only got 3 in there, but basically the cars all have to be traveling in the same direction, and we have to have we can only ever have one truck on the bridge at one time. So the trucks will represent writers, so they need to have exclusive access to our bridge. And here we have an example of the sample output on here. You can see we've got our cars, so we've got up to 3 cars going on and off our bridge. I'm going to actually bring up my sample for this assignment. So if I go and run my code here, you can see that uh, when my program runs, it's actually paused at the moment. It's got some sleeps in there that make sure that it takes time to enter the bridge and to go on and off the bridge. You can see that uh, the cars going in particular directions are actually grabbing access to the bridge, but when the truck started out, it had exclusive access to the bridge. So that will go through and execute. In my sample implementation, I fixed the number of cars and trucks. So I think I've got 10 or 20 cars going on there and a couple of trucks going each way. That's just so that my program ends at some point. If you didn't want to have a limit on the number of vehicles and just wanted your program to run forever, that's fine. So you'll notice when I executed that sample solution there that it actually took a bit of time to execute, and that's because I put a random wait time. So each thread waits. So in this particular context, each thread is a vehicle, um, and so it waits before attempting to enter the bridge, and then it has a wait or a sleep, sorry, as it crosses the bridge. So essentially, that adds some randomness to the simulation that we're creating there. Um, so for this one, make sure you review all of the synchronization problems that we look at, in particular the producers, consumers examples that we've got there, and that will guide you on the development of this, how to actually implement this locking scheme. So you've got the pthread, you've got the pthread create and pthread join to build your threads, and then you've got the mutex lock and mutex unlock functions to build these semaphores, these systems of semaphores. You can also implement systems of conditional waiting as well on your to make your program run more efficiently. So as usual, I've got a tentative marking guide here. So we want your solution to compile and run. We want your solution to achieve parallelism using threads. So we'll be looking for pthread creates and pthread joins. And we're also looking for the locking protocol. So most of the marks in this section will be for getting this protocol modified to work with our cars and trucks problem here. So remember, our cars are going to be readers, but you've got two different classes of readers because it's a one-lane bridge. And we've also got, and you've got our trucks, which are our, again, we've got our trucks going east and our trucks going west. And again, they both need exclusive access to that resource. So they're akin to a read lock. So go through, make sure you don't miss any of the easy marks on the marking scheme as well. So you've got to make sure that your solution is broken down into functions, that you've got a make file, and that you document your code and use consistent indenting. So we've got some guidelines there for you to follow. So if you have any questions on this assignment, please let me know. As usual, I need to get an overall mark of 50% across all assessment tasks to pass COSC 33530. So make sure you put in a good effort on this one to pick up those marks. So that's all I've got for today, guys. Thanks for listening.